All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So we're saying let's replace our loading shown with a single force and a couple moment. Two things at point A. And then we're going to show the resultant force on our sketch that we have here. So let's just jump in and go for it. So if we're doing equivalent loading, which is all this problem is, we have to have the same tendency to translate and to rotate before and after we're moving our forces around. So really, to make sure we have the same translation, we can sum up our forces in the x and y, use them to get a resultant force at a known angle. So let's start there. Once we know that, though, we'll come in and sum up our moments in this original picture about point A and find the moment that it would have caused. We'll stick that on here as a couple moment, and that'll be the end of our problem then. So let's start with our forces. So if I sum forces in the x direction, summing my forces in the x, I'm going to get, well, I have 15 going to the right, so 15. I have 10 going to the left, minus 10. I have this 20 has an x component to it. So plus my x leg of the triangle, 4, divided by the hypotenuse, 5, times the force, 20. Or this total force in the x direction is going to get me to 21 kilonewtons, and it's going to the right. I get a positive out from this, so I'm going to the right. I can then sum forces in the y direction. If I sum up my forces in the y, I have, well, 15 and 10 are only in the x. My 40 is going down, so negative 40. My moment isn't a force, so I leave it off. I have a y component of this force, the 20 kilonewtons. It points downwards, so I will subtract it, minus the y leg of my triangle, 3, divided by the hypotenuse, 5, times our force is 20. Or this is going to get us negative 52 kilonewtons, which is the same thing as saying that's 52 kilonewtons going straight down. But that's my x component and my y component. I can work with those to come in and say, let's get a resultant force figured out from this. So my resultant force, I'm going to call this FR, should be, I'm just looking for a magnitude right now, should be my x component squared, the square root of my x component squared, plus my y component squared, plus 52 squared. And I always put things in as positives into my magnitude calculation because I know, for example, negative 52 squared is the same thing as a positive 52 squared. But I avoid random weird sign errors if I just treat it all as a positive. This is going to get me that my magnitude is 56.08 kilonewtons. I also need to get the direction on that. Magnitude, I need direction here. So let's graph this out. We're basically going to put in an XY coordinate system in here. My origin is in the very middle of that. And I can come in and say, well, let's draw my x component. Always x first. It goes 21 to the right. 21 kilonewtons. From there, my y component comes down. 52 kilonewtons. 52 kilonewtons. The hypotenuse of this triangle that I'm making is going to be the resultant force. This right here is FR, which makes sense. I have a squared plus b squared should give me c squared, or the square root of a squared plus b squared equals c. We have a right triangle we're setting up here. Our right triangle trig, Pythagorean theorem, is going to apply into this. The piece I really need out from that is my angle for my resultant will always measure from the x-axis, positive or negative. We'll get an acute angle from our x component to the resultant. So it's going to go clockwise for this one. And we're going to measure down into the fourth quadrant. We also could have gotten that by saying, well, if I have positive x and negative y, that's the fourth quadrant. It's the same idea in here. Graphically, though, we're figuring this out. That matters for us, though, because when I find my angle, I can say that theta is the inverse tangent of the absolute value of my opposite over adjacent. This is my angle theta. So 52 divided by 21. Basically, what we're doing here is saying it doesn't matter what quadrant I'm really in. My calculator thinks I am in the first quadrant. We can figure out what quadrant it's actually in. Kind of outsmart our calculator. Don't put this in as a negative 52. We're taking the absolute value, just put everything in as positive. And then graphically, we're checking what quadrant are we measuring into. Kind of side steps we need to figure out. Oh, if our calculator tells us like we're negative 50 degrees, where are we actually measuring to? Where are we measuring from? And let's just see exactly what we're doing in here. But that gets us that my theta angle should be 68.01 degrees. So I can come into my sketch down here and add that in. I have a resultant force and an angle. It's going into the fourth quadrant. So it'll come from A, go down into the fourth quadrant. My magnitude here is 56.08. 56.08 kilonewtons. And my angle back up to the x-axis is 68.01 degrees. 68.01 degrees. Which gets my force. Right now I have the exact same tendency to translate this object. My sum of the forces are the same in my original picture and in this updated new sketch. I have a different tendency to rotate though. Right now this would have moment about A. If all I have is a force here at A, I get no moment about A. So to account for that change, let's just come in and sum our moments at A. So with positive going counterclockwise, summing my moments up about point A is going to get me, well, this 40 kilonewtons is going to cause a counterclockwise rotation about A, so it'll show up as positive. Force is 40. My distance is 3 plus 3, the perpendicular distance, or I have a y force, I need an x distance to A, 6 meters. If we go to our 10, it's also going to cause a positive rotation, even though it's a negative force. So we add it in. Plus, my force is 10. This is an x force, so I need a y distance. Going from the force down to A, 5 plus 5 would have a distance of 10. If we check our 15, 15 will cause a clockwise rotation, so we'll subtract it out. Minus my force is 15, and that perpendicular distance is 5. Minus 15 times 5. My couple moment is a moment, so I don't need to multiply by distance in here. But I would say it's clockwise, so let's subtract it. Minus 250. And the last thing I need to account for is this 20 kilonewton force. If I look at its y component, the y component will go straight through A, which means it causes no moment about A. I just need to get my x component in here. It would cause a clockwise rotation about A, so minus fx will be the x leg of the triangle, 4, divided by the hypotenuse, 5, times the force, 20. If I have an x force, I need to multiply by a y distance, 3 meters. So times 3. Or this is going to get me to negative 33 kilonewton meters. That's negative when I assumed it was going counterclockwise. For moments, though, we always report as a positive and give the right direction. So really, this is saying that my total sum of my moments about A is really a positive 33 kilonewton meters. And I'm dropping that negative, so I change my rotation arrow. It's going clockwise. And I just need to stick that into my sketch. I can put it anywhere I want to on here because it's a couple moment. So I'll just come in up above and say this is 33 kilonewton meters. And that'd be my final answer in here. I have now my force and my moment. Between these, I have the same tendency to translate and to rotate the entire object. We have setup and we have an equivalent loading knocked out in this. But hopefully this was a useful video for you. If it was, hit those like and subscribe buttons. Stick around. Let's watch more videos and get you an A with JJ.